what I want to do in this talk is present a novel argument for the impossibility of action at a spacetime distance, with realism about spacetime topology as the main premise. And the way I want to execute this is by proving it the other way around. That is, assume that action at a distance is possible, and that really does involve not assuming something that would rule it out. And I'm also going to assume Occam's razor, and I want to show that these two assumptions lead us to conventionalism about space-time topology. So that's the plan, and like one of the first times I'm trying to sell this to people, so I'm looking forward to objections to this argument. Okay, so let me start out by saying a little bit about space-time topology and why it is that everybody is a realist about space-time topology. Quite generally, for any region, the topological features of a region are those features that are invariant under pulling and twisting, but not under cutting and gluing. So for example, whether or not a region is composed of one connected part rather than multiple disjoint parts, and also whether or not it contains any holes, and if so, how many. Those are topological features. How large a region is, whether it's straight or bent, those are metric features of a region. Now, the way topology usually is presented is that the topology of a space is determined by listing the open sets of the space. So the idea is that an open set is a set that doesn't contain any points on its boundary. So for example, the inside of a sphere is open, but a solid ball that contains all the stuff inside of the sphere and the sphere itself is not open. So we define a topology by specifying the open sets. So suppose X is a set of space-time points. Then a realist about space-time topology claims that there's an objective fact of the matter, how the points in X are located in space-time, and whether or not they form an open set. That is, given a set of points for the realist, there's a fact of the matter about whether or not this set of points contains points on its boundary, whether it's open or closed. Conventionalists about space-time topology are impressed by the fact that there are infinitely many different topologies that we can impose on an infinite set of points. And that the very same set of points X can count as open relative to one topology and not open relative to another topology. Conventionalists think that all these topologies are created equal, and they conclude there's no objective fact of the matter whether or not a given set of space-time points is open or not. We can group them whichever way we want. So those are the two main views, realism and conventionalism about space-time topology. Now, as far as I can tell, nobody is a conventionalist about space-time topology. And here's why. Or here's one reason you might think nobody holds that view, is that it seems that the topology of space-time is just too fundamental a feature to be conventionalist about. For example, the topology of space-time determines whether or not an object moves on a continuous trajectory. By changing the topology that we impose on space-time, we can cut a trajectory into disconnected pieces, which would have an object kind of jump from one point to another. Another feature of space-time that is determined by its topology is the dimension of space-time. We're inclined to think that space-time is four-dimensional, three spatial and one temporal dimension. But by changing the topology, we can give space-time any dimension we like. We can impose a 29-dimensional topology on space-time if we wanted to. Or indeed, we could also, by changing the topology, arrange space-time in a one-dimensional manner. thus eradicating any difference between the spatial and the temporal dimensions of space. If there's only one dimension, you can't have different spatial and temporal directions in space-time. Another feature of space-time that is determined by its topology is whether or not space-time consists of one connected regions or multiple disconnected parts. Indeed, if we choose the so-called discrete topology, which counts every set of space-time points as open, then space-time would be completely disconnected. No space-time point would be connected to any other point. So that suggests that without an objective topology to hold it all together, space-time just dissipates into individual points that we can arrange whichever way we want. So to put it in a slightly breathless manner, conventionalism about space-time topology seems to be a curiously self-defeating thesis that denies the existence of its own subject matter. It's not a claim about space-time, but a roundabout way of denying that space-time exists as a connected unity. So that's by way of motivating why it is that everybody seems to be a realist about space-time topology. I'm not going to say more in defense of realism about space-time topology. Arguments of premises, this one is mine. I will assume that also you will want to be a realist about space-time topology. So I'm not going to say more in defense of it, but I want to distinguish realism about space-time topology from two other theses, with which it otherwise might be confused. One distinction is that realism about space-time topology must be distinguished between realism about the topology of space and time taken separately. If space and time each had an objective topology, three-dimensional spatial topology, one-dimensional temporal topology, then the Cartesian product of the two will be a four-dimensional space-time with an objective product topology. The converse, though, does not hold. The fact that space-time has an objective topology does not entail that space and time separately have objective topologies. As a matter of fact, there are good reasons for thinking that time does not have an objective one-dimensional topology, because if it did, it would induce an objective linear order on all events and thus define an objective simultaneity relation. Objective later than relation. If you have a line, there's going to be objective fact about what is to the left and what is to the right of each point and what kind of coincides. And the theory of relativity suggests that there are no objective standards of simultaneity across space. So that would suggest that there is no objective temporal topology. So realism about space-time topology is strictly weaker than realism about spatial and temporal topology taken separately. Realism about space-time topology must also be distinguished from realism about the metric of space-time. If there's an objective metric, so an objective way of assessing distances between points in space-time, then there's also an objective topology. Any metric on a space induces a topology, the so-called metric topology. Basically, once you have a metric, you can measure distances. Once you can measure distances around each point, you can there's going to be objective fact of a matter of what sort of points are contained in a sphere of a certain radius around the point. So if you take the points inside a sphere, that's going to be your paradigm case of an open set determined by your metric. So metric realism entails topological realism, but not the other way around. So you can be a realist about space-time topology, claim that it exists as this topological connected unity, but deny that there are objective facts about distances between different points in space-time. About space itself, for example, Rudolf Carnap, the early Rudolf Carnap, defended precisely such a combination of topological realism and metric conventionalism that exploit the difference between these two. Okay, so I'm interested in the debate between realism and conventionalism about space-time topology. The question of whether or not there is such an objective topological structure is an instance of a broader question of how much structure space-time has. And there's a consensus amongst contemporary philosophers of physics that question of space-time structure is really an empirical question that gets settled by our best physical theories. Here's the idea. You all know about ontological commitments. A theory's ontological commitments are the kinds of objects that need to exist for the theory to be true. Likewise, you might say that the space-time commitments of a theory is composed of the space-time structure that is needed to distinguish all the physical possibilities postulated by the theory. Well, physical possibilities are models of the theory, modular observational indistinguishability. There's a possibility, you think about all models that are observationally indistinguishable, the class of all those models idea, spelling it out is a little bit tricky. For example, Newtonian mechanics. So can you guys still hear me? My internet connection seems to be unstable. Marius, am I good?
You were cut off for about 10 seconds there.
Should I repeat anything or?
Yeah, maybe the last bit of the slide before, that would be great.
Okay. So space-time commitments theory is the minimal amount of structure that space-time needs to have to distinguish the physical possibilities postulated by the theory. And the idea, and in a second I'll give an example, is that physical possibilities are given by the models of the theory, but modular observational indistinguishability. So we have the theory, it has all these models. We can identify all the models that are observationally indistinguishable. And then we're going to postulate just enough physical structure to distinguish all the other ones. Let me give an example. Newtonian mechanics. One structure that Newtonian mechanics does need is an absolute notion of simultaneity. Because Newton's theory of gravitation is a theory of instantaneous interaction. Gravitational interactions act instantaneously across space. So, for example, I have a mass here, I have a mass there. They attract one another with the force that is proportional to the product of the masses, inversely proportional to the square of the distance. But if I wiggle this mass here, this mass over here immediately feels the effect of my displacing this mass. Yeah, so we have this instantaneous interaction across time. So we need an absolute notion of simultaneity. It's part of the space-time commitments of Newtonian mechanics. But then there's stuff that it doesn't need. So one famous example that Leibniz raises in his correspondence with Samuel Clarke is absolute location. Leibniz says, look, if God took everything in the world and shifted over by 1 meter while preserving the relative distances between all objects, we wouldn't be able to tell the difference. These are two observationally indistinguishable scenarios. Similar example shows us that there's no observable difference between the actual situation we're talking about and one where everything in the world is moving with a constant velocity while preserving all relative distances. So Newton's theory of mechanics has no need for absolute location and no need for absolute velocity. What complicates things a little bit, though, is that Newtonian mechanics does seem to have a need for absolute acceleration. So that's Newton's rotating bucket argument, which claims that you can tell whether or not an object is absolutely accelerated by the presence of inertial forces, such as the ones that you see in rotating a bucket. When you rotate a bucket in absolute space, a bucket full of water, the surface of the water becomes concave. So Newton's rotating bucket argument suggests that we do need an absolute notion of acceleration. So these are some observations about Newtonian mechanics. Turning all of this into a coherent metaphysical picture is a little bit tricky, because Newtonian substantivalism about space would give us absolute acceleration, but it would also give us absolute location and absolute velocity. So it would postulate too much structure. Leibnizian relationism about space, on the other hand, doesn't give us absolute location, doesn't give us absolute velocity, but also doesn't give us absolute acceleration. So it postulates too little structure. Then there's some views in the middle. So Stein's neo-Newtonian space-time has absolute acceleration without absolute location, without absolute velocity, but still has a notion of absolute location in there. So it's a little bit tricky figuring out a view that has just the right amount of space-time commitments. Another problem is that sometimes different theories can adopt different attitudes towards the same structure. One example is the space-time metric. So in special relativity, the space-time metric forms part of the space-time commitments of the theory. It's part of the structure of space-time itself. In the general theory of relativity, the space-time metric becomes a dynamic entity. It measures how space-time is curved, amongst other things. So the metric, in one case, it's part of the structure of space-time. In the other case, it's part of kind of the contents of space-time. In these two theories. I should also mention, for the sake of completeness, absolute simultaneity we saw was needed in Newton's theory of mechanics, but it is famously superfluous in the special theory of relativity, which has no use for an absolute simultaneity notion. So general relativity gets rid of the absolute simultaneity, just the special relativity, also gets rid of the metric as part of the structure of space-time. And indeed, if you look at the history of general relativity, one of the main theoretical motivations for the theory was Albert Einstein's conviction that there really ought not to be any inertial structures. There shouldn't be anything in our physical picture of the world that influences physical processes without in turn being influenced by them. Now, that's why he did not like the fact that the space-time metric in special relativity was this kind of absolute structure. Okay, so this is just by giving you some idea of kind of how tricky it is to determine space-time structure. But there is a popular, kind of very clever, worked out way of trying to adjudicate these issues. That's due, well, mostly due to Michael Friedman and John Ehrman building on earlier work by Anderson. And what they give us is a general method for taking all the realist commitments of a scientific theory and to separate them into what they call absolute and dynamic objects of a theory. And then the proposal is that the space-time commitments of a theory is thus composed of all the absolute objects of the theory. And then they prove some results. The space-time metric is an absolute object in the special theory of relativity, but a dynamic object in the general theory. And also this picture seems to be vindicating Einstein in that general relativity turns out to have no absolute objects at all, no inert structure. So this work, nicely worked out general framework for adjudicating these issues. And you might have hoped that our question about topology of space-time ought to be decidable in the same manner. It concerns space-time structure. Let's us apply this machinery to this question. As it turns out, though, Freeman and Ehrman aren't really prepared for that question. For them, absolute objects are always structures that space-time might possess in addition to its topology. They start out with the unquestioned assumption that there is a four-dimensional spatial manifold, on which they then put all these absolute and dynamic objects. That is, topological realism just gets assumed from the outset. It is never really up for debate. And my question here, one of the questions of this paper is, well, what justifies this preferential treatment of topology? Ought not an objective topology earn its keep in exactly the same way in which other space-time structures do? Maybe by doing some theoretical work. It ought to be a result of our investigation of space-time structure, not an unquestioned assumption. And if there's anything to Einstein's view that there shouldn't be any inert structures in our best physics, should we not even prefer a theory that has also no objective topology as an inert structure? Okay, so now what I want to argue next is that if we take the underlying idea of this approach to determining space-time structure, and we divorce it from its unquestioning commitment to space-time topology, that the same ideas really do in fact lead us straight to conventionalism about space-time topology, unless we make additional metaphysical assumptions. Now, to make this case, I need a view of metaphysics that is frugal, that does not have any metaphysical commitments that would rule out action at a space-time distance. Now, I want to show that how a theory that doesn't adopt what I think it needs to adopt, a prohibition on action at space-time distance, leads us to conventionalism about topology. Luckily, there's a view just like that in the philosophical literature, and that is David Lewis's program of Humean metaphysics. The Humean, according to Lewis, has three main commitments. Lewis's Humean metaphysics is realist about space-time topology. It assumes that there is a spatial manifold. As a matter of fact, he thinks not only is there an objective topology, but there are objective spatial temporal distance relations. But never mind that. So he thinks that these distance relations, he thinks there's an objective metric on the space-time manifold. That means in particular, he thinks that there is an objective metric topology on the spatial temporal manifold. So we have space-time, topologically unified on this picture. And then the world, according to Lewis, is a vast mosaic of local matters of particular fact. So on each space-time point, there are some properties instantiated, and they need nothing more than a point to be instantiated. It's purely local matters of particular fact. Humean metaphysics takes its name from Hume's denial of necessary connections between distinct existences, which Lewis spells out in terms of a recombination principle, that patching together parts of different possible worlds yields another possible world. So we have the canvas, space-time canvas, on which all these properties are sprinkled, that is kind of painted. And if you have two such canvases, you can cut the canvas into pieces and patch together parts of different canvases, and every way of doing so yields another possible world. Okay, suppose we accept all that. And let me define then two things, H and L. H is the history of the world. It's a long list that just tells us which properties are located when and where. For each point in space-time, it tells us what's going on there. That's the history of the world. And then we also have laws of nature, and we can think of laws of nature just as we can identify the laws with the sets of possible histories that it counts as physically possible. Now, laws of nature is as a set of physically possible histories, and the actual history of the world is going to be physically possible by default. So the history and the laws together give us a complete physical description of the actual world. Okay, suppose we have these ingredients. So here on the left-hand side, we have H. So suppose we now take a sub-region of space-time and we divide it into four-dimensional cubes of equal size. And then we permute the cubes by applying an arbitrary permutation. So here on the left-hand side, we have the sub-region contains 9 of these cubes. So we cut into these cubes, and then we just rearrange it to get a different history, H star. By the recombination principle, H star is possible. It's just obtained by patching together different parts of the actual world. So H star, according to the Humean, is a possible history. So we have the original history H and then the permuted history H star. Suppose we do something similar to the laws of nature. That is, we define new laws of nature L star by counting a history as possible, that is possible according to L star, just in case it's the permutation of a history that L counts as possible. So we'll permute the history and we'll permute the laws. Now, so we get another description, W star, of a possible world. According to the realist, W and W star are different possible worlds. An object that moves on a continuous trajectory in H might have its trajectory chopped off into many disconnected pieces that then get rearranged according to W star. The experiences of observers can succeed one another in a different order in H star than they do in H. We have the space-time mechanics. You can also kind of rearrange things in the pole order. Since the realist thinks there are objective facts of the matter about these things, the realist must claim that these are different possible worlds. For the conventionalists, these are just different descriptions of the same possible world. So by the recombination principle, W and W star are both possible. And later on, I will argue that we need to have some metaphysical principles that allow us to rule out W star as impossible. The Humean can't do that. So with these two possible worlds, since they're both possible, they're indistinguishable a priori. But they're also indistinguishable by all possible observations. For example, in W, objects move on continuous trajectories. Objects appear to move on continuous trajectories because they do. In W star, the continuity of trajectories is an illusion created by the laws L star that puts together the dispersed causes of our perceptions like the pieces of a complicated puzzle. Our experiences in the two cases are exactly the same. Just that in one case, what we see is what there is. In the other case, the laws of nature in the world W star systematically mislead us about what's where. Now, so these two scenarios are empirically indistinguishable. So here's an argument for conventionalism. We just do what we do for all space-time structure. We postulate the minimum amount of space-time structure needed to distinguish observationally distinguishable possibilities. Since W and W star are empirically indistinguishable, they're indistinguishable a priori and they're indistinguishable a posteriori. So there's no reason for distinguishing these possibilities in the first place. There is realism about space-time topology overcounts possibility. The minimum amount of space-time structure needed to distinguish all physical possibilities is no space-time structure at all. Okay, that's the argument for the conventionalist. Now you might think, that's, in a way, this is old news. We've just rediscovered the underdetermination of theory by data. And that's really what's going on with W and W star. Yeah, so both of them are empirically indistinguishable, but that just means that in order to choose between W and W star, we also need to take the secondary virtues of these theories into account, in particular, their simplicity. And that the simpler W is confirmed more strongly than the more complicated W star. So, yeah, the empirically indistinguishable means that both are equally confirmed by the evidence. So a purely qualitative account of confirmation can't really distinguish the two. But a quantitative, or at least a comparative account of confirmation does. Yeah, even though W and W star are both confirmed by the evidence, W is confirmed more strongly because it's simpler. It's just the underdetermination of theory by data. This is really what's going on here. So no need for any breathless conclusions. It's a familiar problem. While I think this is quite right, also one thing that's a little bit weird is that we have these two competing simplicity arguments. Because also the conventionalists, it's really applying Occam's razor, saying that the realist has a superfluous structure, and in a sense, a preference for fewer space-time commitments is also a form of a simplicity argument. But really what we have here is we have two different dimensions of simplicity at stake here. One is what you might call simplicity of ingredients. Conventionalism is simpler than realism about space-time topology, in that its commitments are a proper subset of the commitments of realism. And there are few ingredients that you have with your conventionalists. So you can think of that as like the vertical dimension of simplicity, simplicity of ingredients. But there's another notion of simplicity, that's simplicity of arrangement. For example, suppose you have a white canvas and you're distributing kind of continuum many black points. Then there are many different arrangements you can make of these ingredients, the black points and the white canvas. But you might think that they disagree in terms of their simplicity of arrangement. For example, if you take all the points, you make a large black circle. You might think that's a simpler arrangement of the ingredients than if you take all the black points and you reproduce the 1957 New York telephone book. Same ingredients, arranged at different levels of complexity. So likewise, in our case here, W and W star, so the history, okay, let me take one step at a time. History H and history H star are different arrangements of the same ingredients. Yeah, so at most, they differ in terms of their simplicity of arrangement, not in terms of their simplicity of ingredient, because they're the same ingredients. Moreover, also the laws, the simplicity of the laws is really an aggregate measure of all the history, of the simplicity of all the histories that it admits as possible. If, for example, give a standard example, suppose you have two quantities, and you can have different theories about how one quantity varies with the other. A linear dependence is said to be simpler than one that has kind of dependence of with a dependency with higher powers than the polynomial, because they're simpler models. A linear dependence theory has simpler models, and one has a more complicated dependence. So that's the notion of simplicity of arrangement. Now, W and W star at most differ in terms of the simplicity of arrangement. Now, that questions you might have about the notion of simplicity of arrangement, many people have noted that it's not at all clear that there are objective standards for assessing the simplicity of an arrangement itself, rather than measure the syntactic complexity of a description. Syntactic complexity of description is easy, but then there are many cases where the same arrangement can be described in very, very different ways. You can have a syntactically more complicated description and a simple description that both describe the same thing. So these is questions of whether or not we can really measure simplicity of arrangement. Let's put that aside. There are a number of people who think that simplicity of arrangement is an epistemic virtue. That is, there are people who try to spell out what the simplicity of an arrangement consists in, and then try to prove that a simpler account of the available evidence is more likely to be confirmed by future observations than a more complicated rival that makes different predictions. Again, this is the focus often is that you have these two quantities and you have some data points. And the question is why, if the data points look as if they really want to lie on a straight line, why should we draw the line through the few data points in this way rather than have some kind of complicated wiggling up and down? And these people try to give a proof that a simpler way of drawing the line through these data points is actually more likely to be confirmed by future observations than a more complicated rival that makes different predictions. There's not this kind of literature about this stuff. However, even if that is true, it's not really relevant to the problem that we're facing here, because the choice between W and W star is not underdetermined by the available evidence, but by all possible evidence. And can't be that one of them is more likely to be confirmed or falsified by future observations because they make exactly the same predictions. And that's an instance of what I think Sober calls Reichenbach's thesis. Simplicity of arrangement is not a guide to truth when choosing between predictively equivalent theories. And that's what is at stake here. So whatever you might think about simplicity of arrangements being an epistemic virtue that makes it more likely that your theory is going to be confirmed in the future, it's not really applicable to this this case here, because these two theories are the choice between these two theories is underdetermined by all possible evidence. In any case, simplicity of arrangement isn't really all that relevant to our situation here, because the argument for conventionalism is that conventionalism has simpler ingredients than topological realism. It's a straightforward application of Occam's razor. So here we have the two dimensions: simplicity of ingredients, simplicity of arrangements. In the case of conventionalism, there's no, what the conventionalist claims is that W and W star are alternative descriptions of the same possibility, of the same arrangement, which cannot be simpler than itself. So for the conventionalist, differences in simplicity of arrangement, that question doesn't even arise. So the conventionalist is not advocating a weird reform project where we somehow should prefer W star over W, even though W is simpler. No, the conventionalist thinks that there isn't really anything to choose here, that W and W star are alternative descriptions of the same ingredients. So of the same arrangement of very few ingredients. So conventionalism about space-time topology is not a reform project. It's not trying to get you to abandon your favorite theory W in favor of something ridiculously complicated W star. All the conventionalist says is that these are two alternative descriptions of the same possibility. And it recasts theoretical virtues such as simplicity as pragmatic preferences. Given that nothing is at stake in the choice between W and W star, you might as well pick the theory that you find simplest, most pleasing, prettiest, or whatever. These are merely pragmatic preferences. So this argument here, it's the same kind of argument that underlies all the other investigations of space-time structure. It relies on Occam's razor. Now you might have, I mentioned some of the questions about whether or not simplicity of arrangement is a guide to truth. You might also have questions about whether or not applications of Occam's razor are really justified. That's a good question, and not one that I'm going to even try to answer here. All I'm saying is that that's the principle that underlies all these other investigations of all other attempts at extracting metaphysical insight from our best scientific theories. And if we use that principle, you end up with conventionalism about space-time topology. So that's application of Occam's razor. It's not a skeptical argument, right? The conventionalist is not claiming that it's not advancing the epistemological thesis that facts about topology are somehow beyond our ken. You can imagine if an externalist about knowledge. I think it might well be possible for us to have knowledge of topological relations as long as our beliefs about topology reliably track the facts about topology. That's not the conventionalist case. The conventionalist advances the metaphysical thesis that there aren't any facts about topology to begin with, not that they're somehow beyond our ken. So all of this was really by way of making the point that I don't think conventionalism about space-time topology can be defeated on scientific grounds. It's using standard methods for extracting metaphysical insights from our scientific theories. It's using only orthodox methods and not misusing them, as not using any heterodox methods. It's using what everybody else does to arrive at this radical conclusion. So how can we resist the conclusion that there are no facts about space-time topology? If you remember in the beginning, I said, look, we're all realists about space-time topology. Question is, what do we need to take on board so we can remain realists about space-time topology? Here's what I want to propose, what I call the locality principle. Consider the following principle. So we have a cause C, here's the cause C, and in effect E, so C causes E, and there are these two regions, inner region I and outer region O. So the cause C is wholly contained in an inner region I that itself is kind of wholly contained in the region O. So it's region I is an inner part of the region O. So it doesn't share any of the boundaries with O. So I is wholly contained in O. And then E is wholly outside O. So my claim is that if C causes E, and that these two regions I and O, as in the picture, then C's effects must also be had by something in the punctured region that you get by taking the outer region and you take out the inner region, so C with stuff around it, just left with this shell. Whatever causal effect C has on E must also be had by something in the punctured region O minus I. That prohibits C. So if that's not the case, then C would have to act across the gap O minus I to influence E. So by imposing the locality principle, we're prohibiting that. So locality is a way of prohibiting action at a space-time distance. Notice that it's phrased in topological rather than metric terms. And if we accept the locality principle, then the world W star, where we permute the contents of the actual world, can be ruled out as impossible a priori, because by permuting the contents of space-time, you can mess up the locality principle. That is, you can take out. Sorry, let me put it differently. What the locality principle requires is that cause and effect always be connected by a continuous chain of intermediate causes. That's really the upshot of this principle. Now, that you can't find, between C and E, you can't find any gaps in the causal chains that get you from C to E. And a Q permutation, as we had in the case of the permutation argument, would mess up these causal connections, the continuous causal connections. Now, it might well be that if you think about permuting cubes of space-time, that there be some regions of space-time where nothing happens. In that case, replacing one uneventful cube of space-time with another uneventful cube of space-time wouldn't make any difference. That's why it's important that W also contains the description of the laws of nature. As long as it is possible for any region of space-time to host some relata of causal relations, then W star can be ruled out as impossible, because the laws of nature would violate the locality principle. So that's why I always drag the laws of nature along. It's really, the locality principle is really a constraint on the laws of nature. It's also a constraint on the actual history of the world, which is physically possible by default, but it's a constraint on the laws of nature. Okay, so if we accept the locality principle, then we can rule out W star as impossible a priori. Let me say a few things about the locality principle and then move towards wrapping things up. Everybody thinks, or most people think that cause and effect cannot be located in disconnected space-time regions. You get that in Lewis's modal realism, where with all these possible worlds, all equally real, but they're spatio-temporally separated from one another, like raisins in a pudding. Now, there aren't any spatio-temporal relations that go from one world to another. And so these are disconnected space-time regions, different possible worlds, and there aren't any causal relations between the two. So everybody agrees that if one thing and another are in disconnected spatio-temporal regions, if there's no continuous space-time path that leads from one to the other, then there can't be any causal relations between them. What the locality principle really says is that an unused spatio-temporal connection rules out causal relations just as much as a missing connection. Now, it's a view on which the topology of space-time constitutes the manifest possibilities of causation. For one thing to cause another, it has to kind of make use of one of these continuous connections between the two. Okay, so that's the locality principle. It's a topological principle, not a metric one. And I didn't really get into that. It's formulated in a way so that it avoids certain technical problems with Hume's contiguity requirement on causation. And also say it's not an acceptability condition on scientific theories. That is, a scientific theories, there can be good scientific theories that are only interested, there can be good scientific explanation, good scientific theories that are only interested in some of the causal factors at play, rather than spell out complete causal chains that connect different events. It might only be concerned with fewer with fewer parameters that are easier to be manipulated by us. Sappes makes a point that such theories abound in the social sciences. If you think about how we argue how a person's present beliefs are influenced by her past experiences, they usually have the experiences, then we have the present beliefs, and a theory might not say anything about the temporal gap between the two. So you can have a good psychological theory that doesn't describe complete causal chains between spatially temporally disconnected causal effects. So it's not an acceptability condition on scientific theories. There can be good explanations that are kind of spatially temporally gappy. All that the locality principle claims is that such explanations are undermined by the discovery that there aren't any connecting causal chains. Okay, so let me just say one thing. So that's a locality principle. I think we ought to accept the locality principle. I said a little bit about why it might be kind of intuitively plausible. That's not the argument. The argument is that you ought to accept the locality principle because it allows you to rule out W star on a priori grounds. It helps the topological realist to resolve the permutation problem, and thus allows you to remain a topological realist. That's why you should accept the locality principle, because it supports realism about space-time topology. Okay, 3 quick concluding remarks. Offhand, you might have thought that the following 2 are different theses. First is that causation is necessarily local. That's the locality principle. Second one is what I think is a much weaker thesis, that there are facts about whether or not causation is local. On my view, there isn't really much of a difference between the 2. That is, to give a counterexample to the locality principle, you would have to find a cause and an effect. And in 2 regions, the inner region E and the outer region O, such as nothing in O minus I, the punctured region that plays C's causal role vis-a-vis E. Well, that counterexample already assumes that the objective facts about of the matter, which regions are inner parts of which other regions. That is, any counterexample to the locality principle already assumes realism about space-time topology. That is, assumes the very principle that is that if I'm right, underwrites realism about space-time topology in the first place. So if the argument is right, that the only way you can have, the only way you can be a realist about space-time topology is by ruling out the possibility of action at a distance, in which case there is not going to be much daylight between these 2 theses. The only plausible theory on which the facts about whether or not causation is local is one which rules out non-local causal interactions. Now, if accepted, this also has immediate impact on Humean metaphysics. So the Humean accepts realism about space-time topology, but I've argued that that requires the locality principle, which contradicts the recombination principle. Now, the argument from realism about space-time topology to the locality principle involved an appeal to Occam's razor. So the claim isn't that denying the locality principle is self-contradictory. If you look at Samuel Clarke, Clarke thought that action at a distance was self-contradictory because it required an object to act where it is not. So he thought that as an analytic truth that action at a distance is impossible. That's not the view I'm defending here. So the argument proceeds by Occam's razor. Well, that's good enough because it means that we can, if we accept Occam's razor, we can know a priori that there's no plausible metaphysical position on which there's action at a distance. So if that's true, then human metaphysics is theoretically unstable. And the topological realism it assumes conflicts with the recombination principle, which is the very thing that makes human metaphysics human, and the denial of necessary connections. Okay, so all of this leaves a lot of questions open. I haven't said anything about the status of Occam's razor, which I liberally applied. I raised some questions about whether or not simplicity of arrangement is an epistemic virtue, but I haven't asked any questions about Occam's razor, just assumed that. I've also said nothing about the nature of space and time, or about the nature of causation, or about the source of gnomic necessity. All of these open questions, I've said nothing about them. All I try to argue here is that realism about space-time topology. So, this sentence is all messed up. Ignore this sentence. Realism about space-time topology have good reasons for denying the possibility of action at a spatial-temporal distance. That is, I've tried to defend an argument that has this one premise, realism about space-time topology, and the conclusion is that is the impossibility of action at a spatial-temporal distance. So that's all I've tried to do here, and that's all I got. Thank you very much.